Building technology-focused communities, bringing together organizations of all sizes and experts from varying backgrounds, moving industry standards forward and advancing cutting-edge technologies through open, time-tested processes to identify technically and commercially sound solutions to shared industry challenges. Since 1989, the vendor-neutral, not-for-profit Object Management Group has facilitated these objectives on a global scale. You'll find our standards implemented across land, sea, and beyond, on your smartphones, in your transaction receipts, even on the International Space Station. Today, our standards innovation continues through the OMG Standards Development Organization, developing enterprise-grade standards and technical specifications, certifications, and more. In parallel, we're driving digital transformation across ecosystems with our growing portfolio of targeted consortia. And all of this, it's driven by you, the experts. Where is technology going? You decide. And together, we'll tackle new industry challenges. OMG, building technology communities. By you, for you, about you.
My name is Sanford Friedenthal. My colleague Ed Seidewitz is here, and the two of us are going to be presenting SysML v2, where we are and how we got here. Ed and I were co-leads of the SysML v2 submission team that produced the 3 specifications that compose the SysML v2 submission. Okay, so I'll be presenting part 1. I'll go over some little bit of background, and then I'm going to focus on a comparison between SysML v2 and SysML v1. And then I'll briefly describe some considerations for transitioning from SysML v1 to v2 and a brief summary. Ed will then come up and talk about, in the second part, about some of the key language design principles and the rationale for some of our key design decisions. For the purposes of this presentation, you'll see some representations of SysML v2, and you'll see both the textual syntax and the graphical syntax. The textual syntax was created using our open source pilot implementation. This was developed as part of the submission. It was used to validate the specification. So we'll be using or referring to that for the textual notation, and for the graphical notation, we used an open source capability called Plant UML that was modified for the pilot implementation. The graphical notation is not of commercial quality yet, but the textual representation is what you would see in an actual tool. And just briefly, some background. So let me just start with just a little context. This slide and this statement, the future of system engineering is model-based, that comes directly from the INCOSE Systems Engineering Vision 2035. And in that vision, they talk very much about, emphasize model-based system engineering as the future for system engineering, as being part of the digital transformation. As we move forward, the emphasis will be to expand the scope of model-based system engineering. So it's going to encompass the full life cycle of a system development, and it's also going to encompass from system of system level all the way down to component level. So sort of these 2 dimensions, and that's a major emphasis on where we're headed with MBSE. But we also want to ensure that our MBSE approaches are complemented by agile processes. I don't necessarily mean agile in the same sense that we use it for software, but we think about agile system development, including automated workflows and configuration management of the digital thread, where the digital thread represents a whole series of different engineering artifacts that are in fact connected to and traceable to one another across the life cycle. Also, part of this vision, if you will, for MBSE is that we really begin to leverage model patterns and reuse and other aspects to enable MBSE. So what we get out of that and what we're trying to achieve is we want to clearly be able to manage the complexity and risk associated with our evolving systems. We want to be able to more rapidly respond to changes in requirements, changes in design. We want to enable the reuse and design evolution and make that a much more effective process. We want to have the capability to reason about our systems and analyze them in various ways. Of course, from the beginning, we want this shared stakeholder understanding, all the different stakeholders involved in the development process. So MBSE enables that. And we want to have the ability to do automated documentation and reporting. And some of this capability clearly exists today, so it's a question of extending it and expanding the scope of MBSE and doing this job better. So let's just take a quick look at SysML, the system modeling language. It supports the typical system engineering activities from requirements through system level design and analysis, verification, validation across the life cycle. SysML has evolved from when it was originally introduced back in 2006. Came out as version 1.0 formally actually in 2007. And then it was incrementally updated through the OMG revision task force process. And so there were dot releases that occurred roughly every 2 years. So our most recent dot release for SysML v1 is version 1.7, and that just came out at the end of this last year. And we anticipate that being the last version of SysML version 1 series before moving to SysML v2. Over that period of time, SysML v1, if you look back at the beginning in 2006 and where MBSE was, you can see that it had a big impact. It facilitated awareness of MBSE and the adoption of MBSE across large swaths of industry. And over that period of time, we've learned a lot. So we've learned how to apply SysML for MBSE. We've learned what works, what doesn't work. And based on that, we use what we learned from SysML v1 as a basis for moving towards SysML v2 and addressing many of the limitations that we encountered with SysML v1. So let's just take a quick look at the status of SysML v2. In February of this year, we submitted our what we call our final submission. It turns into alpha specifications. And we basically did a presentation to the OMG, did the final presentation in March. And we formed what is called the finalization task force. And right now we're awaiting the OMG Board of Directors approval, and once that occurs, we will have a beta spec. We're anticipating that to occur over really in the next week or two. So we're very close to having the beta spec, and we go forward from that, and during this finalization phase, we have an opportunity for the vendors, tool vendors that are implementing SysML v2 to raise issues against the specification. And we can get those issues addressed through this finalization phase. And then next year, basically move into the final adoption of SysML v2. So we're anticipating that to occur sometime mid-year. So now let me, with that as a little backdrop, let's go in and talk about SysML v2 and how it compares with SysML v1. So let's start with just what our objectives are for v2, because our objectives are stated relative to what we had with SysML v1. So we're really trying to increase both the adoption of MBSE and the effectiveness of our MBSE with SysML. over what we had with V1. And you can see a series of sub-bullets there. Those are all the areas that we're trying to make improvements. Yep. So for example, we want to improve the precision of the language, make it more precise, less ambiguous. We want to make it more expressive. We want to ensure a more consistent language, more regular, and you'll see I'll come back to these items in a few slides. We want to improve the interoperability of the systems model, system modeling tools with other models and tools in the engineering ecosystem. We want to improve usability by both the folks that develop the models and those that consume the models. We want to make SysML more extensible, even though it has a good extension mechanism through profiles and stereotypes today. We want to further improve that so we can apply the language to domain-specific applications. And then, of course, we want to maintain a migration path from SysML v1 to SysML v2. So these are what we're trying to accomplish. So in order to do that, if you take a step back and contrast SysML v2 with SysML v1, the first thing you'll see is that we developed a new meta model. Whereas SysML v1 was based on UML, SysML v2 is based on this new meta model that is not constrained by UML. However, it leverages much of what was learned from UML. So we have much of the UML modeling capabilities in this new meta model, but it's targeted towards system modeling. And it's also grounded in formal semantics. We've done that from the beginning. The other area we've made significant improvements in and will continue to make improvements is in the area of visualization. SysML v1 had 9 diagrams. We did have supported tabular representations of the data. In SysML v2, we have similar kinds of diagrams as a starting point, also the tabular views, but we also have a textual notation, which I'll show you, and we find this combination of the graphical representation and the textual notation to be a very, very complementary. We also have the ability with this very flexible view and viewpoint mechanism to go well beyond what we had in the 9 graphical diagrams for SysML v1 and perhaps make much more interesting visualizations. And we're looking forward to that. We look to the tool vendors to really exercise this capability and think about things like 3D graph visualizations and things of that sort. So we don't have that to demonstrate right now, but we're looking forward to seeing that in the tool vendor implementations. And then the third major area that changed is we introduced a standardized API to access the model. So in SysML v1, there was no API. There was no standard API. Every tool vendor had their own. They updated it with different versions. Documentation was variable. In SysML v2, we have one standardized API with a set of services that allow you to access the model, query it, navigate it, update it, and the like. I have one slide on that later. But now let me go into a little bit more detail in these different areas. So first, let me just talk about the basic capabilities of the language. This is similar, if you look at SysML v2, it looks similar to what we had in v1 at this level. We had behavior, we had structure, we had requirements. We also had what we called parametrics. So we referred to those as the 4 pillars. Well, we have something similar here. We do have behavior, we have structure, requirements. In place of parametrics, we have analysis. And you can see there, one of the things that stands out is an expression language. We did not have that in v1, but in v2, we have an expression language so that we can specify analysis much more precisely. We have a more robust verification capability. When we look one level below this level is where you start to see the differences. So at this level, a lot of the v1 concepts move forward into v2. But we'll go in, and now I'll start to, you'll see at sort of the next level where the differences are. Let's start with the textual representation. And let me just take this very simple model fragment, and let's just talk through it. So you have a part called vehicle, and you can see it has an attribute called mass. And also you see that that mass equals the engine's mass, engine.mass, and the transmit plus the transmission's mass, or transmission.mass. Right off the bat, you see this use of the expression language, which didn't exist in V1. So we can very precisely say, in this very simple example, the mass is the sum of those two masses. We see it has an action called provide power, which means provide power to the wheels. So the vehicle performs the provide power action. It has a couple of parts. It has an engine part, which in turn has an attribute of mass. The engine has a port called torque out port, and it performs a action itself, which is to generate torque. You see the transmission similarly has an attribute, a port, and it also performs an action to amplify torque. And then you see a connect statement there between the engine's port and the transmission's port. And then below that you see an action called provide power, which has two nested actions, one called generate torque, one called amplify torque. And in fact, those are the two actions that are being referenced by the engine. You can see the engine performs the generate torque, and the transmission is performing the amplify torque. So we're connecting the parts structure and that behavior that's described below. If you advance, what you can see graphically is the part vehicles over there on the right. You see the mass equals the engine.mass plus transition.mass. You see the two parts, the engine and transmission, although you don't see the details for the engine and transmission like you do over in the textual side. You see the actions the action that the vehicle performs, which is to provide power. And there's a little symbology following that, which we won't go into, but at any rate, you can start to see how the graphical syntax just is a complement to the textual syntax. They are complements of one another. If you click again, you can see this is an example of the connect statement there, where you can see the engine.torqueout port. You can see it graphically. There's the engine with its torque out port is connected to the transmission's torque in port. So there's the way in which you establish that connection. Again, the complementary nature of the graphical and textual. And finally, one more. You'll see the provide power there, and you see it's composed of the two actions, generate torque and amplify torque. So what we have is a language now with a very precise textual syntax and a complete correspondence with the graphical syntax. And this, I think, we'll find very, very useful. So as tool vendors implement both, a user will have the opportunity to use the graphical syntax only, the textual syntax only, or more likely, both. Next slide. So that was one of the key differences you see right off is the introduction of the textual syntax. Now I want to go into another really key difference. And this is this notion of definition and usage. And there's this consistent pattern of definition and usage that we use in V2 that was introduced in V1, but more informally. So the idea behind a definition and usage is you define an element one time, but then you can reuse it in many different contexts. So you define it once, and then you can use it many times. And we'll see examples of that. As I mentioned, SysML v1 informally introduced this concept. For example, a block is a definition element, and a part property is a usage of a block. But what you find is that concept of definition and usage was applied in an irregular way across the language. So it somewhat applied to activities, it did not apply to requirements, and so it just basically somewhat inconsistent. On the other hand, in V2, as I said, it's formally part of the language. So there is actually within the meta model itself, there is a concept of a definition element and a usage element, and it applies to virtually all concepts in SysML V2. And so it's a very consistent, regular pattern, and I'll show examples of that. And what it allows you to do is virtually any concept, you can, whether it be a part, or an action, or a requirement, you can decompose it in exactly the same way. You can specialize it in exactly the same way. And other operations, if you will, or aspects of the language, they're treated in exactly the same way. So it's very, very regular. And what does this give you? Well, first of all, it's really improving our ability to reuse, because we have this definition that we can reuse consistently. It's easier to learn, and it also enables automation. So we get a lot of benefit from this pattern. On the next slide, this is just a partial example showing the terminology that also was modified to reflect the definition and usage pattern. So on the right, you see, for example, part property and block, whereas on the left, you see part and part def. So part def is short for part definition, and part, in effect, is short for part usage. So we have this very simple terminology, part and part def, and if you go down those two columns, you can see that in SysML v2, you see a very consistent terminology, for example, port and port def, action and action def, constraint and constraint def, etc. And if you contrast that with SysML v1, you can see the differences in the terminology. So once again, just makes it much more straightforward to use, to learn, and it behaves in this very regular way. Now let's look at one example here. I'll just show in SysML v1, this is how we would decompose, in this case, this vehicle. So I have a context block there. I put my vehicle 1 into the context. So its context is composed of vehicle 1. And now you can see lowercase vehicle 1 is the part, and it's typed by the block vehicle 1. So if I want to go to the next level of decomposition, I go from the vehicle 1 block to the engine, lowercase engine, which is typed by the engine block, and I go to the transmission, lowercase transmission, typed by the transmission block, etc. So at each level of decomposition, you go from block to a part property that's typed by a block, and then that block, in turn, has part properties that are typed by other blocks. So you stagger back and forth, block to property to block to property to move down your decomposition. Let's contrast that with what you can do in SysML v2. You can create a decomposition similar to v1 if you want, but a more natural way to decompose in SysML v2 is directly with parts. So what you see here is you see vehicle 1 is composed of an engine and transmission, and the front axle assembly and rear axle assembly, and you can see the front axle assembly decomposes further, and the front wheel assembly further decomposes. It's part to part to part to part. So the decomposition is just down a parts tree, which is obviously a very natural way for engineers and system engineers to think about their system, as opposed to going block to part to block to part. The other thing is it also lends itself towards modifying your design more readily than we had the capability to do in v1. So if you look at the block decomposition on the left, we have a tire at the bottom, and we've specialized it into a front tire and a rear tire, and those are two blocks that are specializations. And what we wanted to do was to modify the tire pressure on the front tire and the rear tire, And in order to do that, we had to create these two specialized blocks and what's called redefine the pressure, override it and put a value on it. Well, we do something similar in V2, but if you hit again, you'll see that it's a little bit more straightforward. So here I want to reuse tire, so I've got a part def called tire, and then I just create my tire and redefine the value. And I didn't have to create the two additional blocks for front tire and rear tire. And as your system gets more complex, this just makes it much easier to modify your design configuration, is what you'll see. So it's very, very powerful capability. Let me just highlight a few differences. I'm clearly not able to go into all the differences here. I'm just highlighting some. But let's talk about a SysML v2 requirement, and we'll contrast it with SysML v1. In SysML v1 requirement, we had a requirement contained a shall statement, a text statement, if you will, where you'd state the requirement in text. It also had an ID. So we had an ID and a text statement. We could add other aspects to it if we wanted to. But well into the development of SysML, I think it was version 1.5, we introduced the notion of a property-based requirement where we could add properties to the requirement. But it was a non-normative extension of the language, and it was still somewhat cumbersome to include that. So what we did in V2 is we just made every requirement in effect a property-based requirement. We leveraged that idea, but we built it into the language. So a requirement is a kind of constraint that any valid design solution must satisfy. And so what you're looking at on the right is you've got the vehicle specification composed of this mass requirement, and you can see it has an identifier there, which is just the number 1. And you can see it has the shall statement. The actual vehicle shall be less than the required, the actual vehicle mass shall be less than the required vehicle mass. That's fine, that's a typical statement of requirement. But we've also introduced, if you can see the require down there, that's a formal constraint that says the mass actual must be less than the mass required. And now the importance of that is that you can evaluate that constraint. So if you ran an analysis, you can compare and evaluate whether that constraint holds or not. And so all of our requirements have this capability. You may only choose to apply it in certain select cases, maybe for critical performance measures and the like, and in other cases just use the standard text requirement, but you have this capability built into the language. Another distinction, if you're familiar with V1, you're aware of the concept of instances or instance specifications actually. And so here I have an example of a vehicle, and it has a vehicle block, and it has a value property called VIN, or vehicle identification number. It's typed by an integer. And now I want to create a particular vehicle. So I create this vehicle 1 underlined over on the right-hand side, if you can point to that. And I give it a particular VIN number. So now we've, in effect, identified, if you will, you could think of it as a unique vehicle, or the intent is that it represents a unique vehicle. But now I want to talk about that unique vehicle, and I want to talk about its speed at different points in time. So what I've done is I've created additional instances or instance specifications where you can see the first one I call vehicle 1 T0, and you can see it has a time equal to 0 and a speed equal to 0. The mass in this case isn't changing. And then I have another instance spec called vehicle T1 at time t equal to 5 seconds with the speed equal to 30. So basically I'm taking this individual vehicle called vehicle 1 and I'm looking at its values of its properties at different points in time. But there's no distinction in this concept. And I'll show you what it looks like in V2, and you can see the potential, significant improvement. So in V2, we have the ability to create what's called an individual vehicle. So here, this is vehicle 1 is an individual vehicle. And what you see is it has a VIN equal to 1. But then you see below it what are called snapshots. There's 2 snapshots, one at T0 and one at T1. So these are points in this case at T0 and T1, points in the vehicle 1's lifetime. And at each point in the lifetime, we can see values of its properties. So you can see speed equals 0 and speed equals 30 kilometers per hour in T1. And so the bottom line is we have the ability to talk about an individual thing, and then we can talk about the state of that individual thing at different points in its lifetime. And they're called snapshots. We can also talk about a period of time for that individual thing as a time slice as opposed to a snapshot. So if I wanted to talk about the state of this vehicle 1 from T0 to T1, I could create a time slice for that as well. So that's a real important point, that SysML v2 has a real underlying semantic here that distinguishes the concept of an individual and the points. It has a lifetime, and you can talk about points in its lifetime and the state of that vehicle as it evolves across its lifetime. Another item where you can contrast with V1, if you look at this part def, you see it's called Sport Utility Vehicle. But in V2, we have the ability to create an alias. So I want to create an alias called SUV to use that name in place of Sport Utility Vehicle. So I've just defined it right there, alias SUV for Sport Utility Vehicle. And now, in the next one below that, you can see I have a part. If you hit it again, you can see that the part has a unique, what we call a short name, and it's called 1.1, should be in quotes, but at any rate, 1.1, and that's any element in the language can have a short name, not just requirements. Anything can have a short name, and you can basically give it any name you want. But here, I called it 1.1 as its short name. I gave its regular name as lowercase SUV, and I typed it by its alias name, SUV, in all caps. So there's an example where you have a lot of flexibility in terms of your naming, and you can have different names for the same thing. And it's very, very useful. It provides a lot of flexibility. I believe the last highlight I want to, or difference I want to highlight here is in the extension mechanism itself. On the left-hand side, you see the way we can extend the language. So we have built in, obviously, to SysML v1 is a concept of a block. But let's say I want to further extend that concept, and I want to create what's called a stereotype called hardware. So I can create that. It's not shown here, but there's a way to create a hardware stereotype. And then I want to apply that stereotype to this processor element. So that's what you're seeing there. I've applied the hardware stereotype to the processor so I can designate it as an element of hardware. But I also want to take that processor and note that it is a subclass of this hardware item. And every hardware item has a mass. So you can see that the processor now inherits the mass property. So anytime I want to create a hardware item, I can specialize the hardware item block that you see there, and I can apply the hardware stereotype. So that's more or less what I have to go through in order to do this. Now, in addition, bear with me one moment. In addition, you'll notice on the processor, I've got some additional what are called tag values or stereotype properties where you can see that I've said that the age of the processor is 11. let's say 11 years. And the manufacturer of the processor is Mercury Systems. And these properties are different than mass. They're like metadata about the processor. So they're a different kind of property. We call them, again, stereotype properties. I can do this very same thing, but I can do it in a more robust way and actually a more or less simpler way in V2. And what you're seeing on the left is an example. I'm not showing you how I created the stereotype. That I have to show you a different figure. But you can see the results of applying the hardware stereotype to the processor. Again, I get the inherited mass that you see there. And you can see the stereotype properties, or the equivalent of stereotype properties. You see the manufacturer and the age. Furthermore, you see the constraint with an actual constraint expression called age is less than 10. Interestingly, in this case, the age is 11, so it violates this constraint. And we would expect a tool, a proper tool, to, for example, turn something red and notify the user that you've violated the constraint. But the bottom line is, I can create very sophisticated extensions. I don't need quite as much machinery as I needed on the left-hand side in V1, and I have more capability which goes beyond what I can describe here right now, but a lot more capability to provide these domain-specific extensions. Okay, so I'll just kind of wrap up this portion by saying, let's just look at a very simple fragment of a vehicle model just to get a sense. So you recall before I had the vehicle specification with the mass requirement. I didn't include all the details of the mass requirement, just the name and ID that you see there. And then if you select it again, there's my vehicle, and you can see it has a set of various attributes. It has some ports. It performs the action that we talked about before. It has some states called vehicle states. And then if you select it again, you can see what those vehicle states are. So you see the state representation down below, and you can see that the vehicle states, it has an off state and on state. In the on state, you can see it has entry, due, and exit behaviors similar to what we have in V1. And you can see the transitions actually have parsable, evaluatable expressions on them for their guard conditions. So it's a very precise representation of states. And here you see also a verification case called mass test. Happens to be a simple one, but it's verifying that requirement, and it has, I know it's you probably can't read it, but it has objectives for this mass test. It states the actions for this mass test. It tells you the kind of verification method it is. It's a test as opposed to an analysis or an inspection. So it's quite a robust capability for defining verification cases and verification information. So this is just a simple example where you see some different aspects of this vehicle brought together. It clearly can be expanded into many, many other aspects of the design and specification. So that I'll kind of conclude sort of the language side. I want to have this one slide on the API. And just note that what you see in the center here is the SysML v2 repository. I've just indicated as having the structure, the behavior, the requirements, all the kinds of things that we've been talking about, analysis, verification. Comprehensive system model is reflected there. And then you see the system modeling API around it, providing the interface to that repository of data. And you see that this is just to highlight some of the kinds of applications that can start to interface to the SysML model through the standardized API. So we see an example of a CAD viewer that's accessing the system model. And by the way, the system model can actually represent geometry. It's not intended to be a CAD model, but it can formally represent geometry such that you might do in an early conceptual phase, or to define keep-out zones and things of that sort. So in this first case, again, CAD viewer application pulls the geometry out and renders it in the viewer. You see the second application. It was actually demonstrated. It's an analysis tool called Maple, and it's a very sophisticated solver, analytical solver. Again, the equations were incorporated into the SysML v2 model using the expression language. They were extracted through the API into the solver and then solved. You see an application on the lower left there for graph visualization. Again, this is using something we've been using right along, an application called Tom Sawyer. That's what they do specifically, is graph visualization. They use the API, go into the model, extract the information, and render it. And then another example here is an application called Sandia by Intercax, where they, again, go into the model through the standard API, pull the data out, and then apply versioning services to it and begin to create a digital thread. So what you're seeing is actually an integration with a whole series of other engineering artifacts that were outside of the SysML model, but it gets integrated in to this digital thread. So these are just some examples of various applications that can take advantage of the API and access the data in the SysML v2 model, pull it out, operate on it, do things to it, and by the way, make updates to the system model through that API. So a lot of potential capability to have SysML v2 be really integrated into the overall model-based engineering and digital engineering ecosystem. So I'm going to go into this next section. Well, let me go through this one slide here just to take a step back, do the comparison, and I'm not going to go through all the details of this, but just note that we said we wanted to make SysML v2 more usable. We think we've accomplished that, made it simpler to learn and use. Not to say that it's simple. It's still a very complex language, but I personally believe that practitioners can come in, people who understand system engineering can come in and learn the base portions of this language so that they could be relatively productive fairly quickly. Now, once you've learned that, it will take you more time to take advantage of the full language, but I believe that because of the regular nature of the language that I referred to, the definition and usage pattern, the consistent terminology and other aspects, the ability to just decompose parts as opposed to go and block part, all these kind of things make it simpler to learn and to use. I think you can start to see, hopefully from this presentation, you get indications that it's more precise, that we've introduced this textual syntax that's just inherently more precise. We've got an expression language. We have the formal semantic grounding, which I didn't go into much, but I talked a little bit about the snapshots and the lifetime and what have you. We have requirements as constraints. Overall, it's a much more precise language. It's more expressive. Again, there were a couple of these areas that I mentioned and many that I did not. For example, we have the ability to model, support variant modeling. We have concepts of, for example, variation point and variant and variability constraints. So we can model variation. We have concepts of trade-off analysis. I mentioned individuals and snapshots. I mentioned simple geometry and many other aspects. It's more extensible. I showed you that comparison between the two. Hopefully you start to see that there's a very, very capable extension mechanism that's very, very powerful and more interoperable, as you started to see through the standardized API. So this just generally, I think we've made a lot of I think we've achieved the objectives that we set out to with SysML v2 by making these kinds of improvements. I'm going to switch gears and I want to talk about the transition from v1 to v2 and some of the things to think about. Although we're, let's say, roughly a year away from having the final adopted spec, tool vendors are implementing this specification as we speak. You'll be hearing more from the vendors in the near term, and you'll start to see what this looks like in commercial tools. So let's talk a little bit about the transition. It's really important to start your planning now. If you're using V1 and you want to start using V2, it's not going to be a push the button and just overnight you're going to go from V1 to V2. You need to plan it. So what you want to do is take advantage of your improvement teams that already exist. A lot of organizations have digital engineering improvement teams, model-based system engineering improvement teams of various kinds, various communities of practice, and have them start to take a look at SysML v2. Begin to get familiar with it. And perhaps initiate some pilots using you could start using our open source environment, or you can begin to talk to you should begin to talk to your tool vendors and maybe even get involved in their early implementations and just start to use it, provide your tool vendors with feedback. And then, as you do these pilots and you learn and you start to assess the impact on your practices, which hopefully will be, you'll see opportunities to improve them substantially, you'll begin to prepare plans to update your practices. And you don't need to do that wholesale, all at one shot. You can start to do this somewhat incrementally. For example, going from block decomposition to part decomposition, what are the implications of that? And look at your updates to what is going to be required of your tool infrastructure. It's not just your modeling tool, it's plugins and the like, your training, your metrics, your reference models. There's a lot of aspects to this. And then start thinking about, okay, as we update our organizational practices, let's start thinking about which projects do we want to deploy this on. It's not going to be every project, every SysML v1 project. You may choose a new program that's starting up as an opportunity to deploy SysML v2. Or you may take, maybe it's at a particular milestone and it's appropriate to look at that point, introducing SysML v2 on that project. You want to think that through and do it carefully. I want to mention that the DoD Office of Digital Engineering, Modeling, and Simulation under Daniel Hetema, who's the director of that office, he is developing what he calls transition guidance. And it's basically intended to help not only the Department of Defense and the services, but also the broader community outside of the Department of Defense, and provide guidance on how one goes about transitioning from V1 to V2. As part of our specification to enable this process, we also did develop a transformation specification such that if you have a conformant SysML v1 model and a tool vendor provides an implementation of this transformation, you can go from your v1 model and transform it to a conformant v2 model. So this will basically really facilitate the moving of existing v1 models to v2 so that you don't lose obviously all the investment that you had in v1. I do want to say that the transformation that you're shown here is just the first step. Probably going to have to do some additional refactoring of your SysML v2 model in order to really take advantage of SysML v2. So you'll move it over by doing this sort of direct translation, and then you'll have some additional changes. So it's non-trivial, but this should help a lot in preserving the investment that you have. I want to kind of wrap up with this slide here. And just talk about as we move to V2, think of this as an opportunity. SysML V1 has been out there, as I said up front, for 15, 18 years, whatever it's been, since 2006, so long time. And over that time, I said we've learned a lot. But we can do a lot better with our modeling. We can really, this V2 gives us an opportunity to be more rigorous with our models. At the same time, making them more usable, more expressive, more, all the improvements that I've already described. But it's a real opportunity to bring rigor to our MBSE process and ensure that our models do what they're intended to do. And we really have to take advantage of that. And so in order to do that, you know, you're clearly still going to be able to take a V2 model and you could, you know, if you can create a lousy model, no matter what the, you know, a fool with a tool is still a fool. So you can still create a poor model. So what we really need to do is take advantage and bring rigor and make sure our training material is high quality, bring certification process, not only the practitioners, but to instructors, make sure our guidelines and our patterns and our practices are rigorous, ensure that our tools have the proper validation suites to make sure that we have construct proper models, bring in review processes that are also rigorous, et cetera, et cetera, et cetera. The bottom line here, let's take advantage of this as a real opportunity to create this culture of quality in our modeling efforts. So let me summarize and just say that SysML v1 has served us well. It's based on UML. UML, of course, was designed as a software modeling language. We took advantage of that early on, which was a good move. And we learned a ton from it, and we accomplished a lot with it. I say we, I mean the community at large. And now we've gone to V2, or we're in the process of going to V2, where we're addressing the limitations based on what we learned over the last many years. And we have the opportunity to really improve the adoption of MBSE and the effectiveness. As we've gone through, we have a new meta model. We have this graphical and textual syntax. We have a standardized API. Those are really key features of SysML v2. As a result of that, we have a language that's more precise, more expressive, more usable, more interoperable, more extensible, more regular, as I emphasized, and that's this consistent definition and usage pattern really helps in the ways that are noted there. We're about to have approval of the beta spec and anticipate the formal and final adoption next year. And what we anticipate after we get the specification, the final spec, we'll continue to evolve the spec based on user feedback, vendor feedback, and new evolving requirements. For example, domain-specific extensions to the language. So we expect a lot to be done to be creating libraries of domain-specific extensions. And the last point here is if you're using V1 or if you're not using V1, start to begin your plan for transitioning to V2. And think of this as an opportunity to advance your MBSE capability and an opportunity to really improve our model quality.
So that was a great overview, wasn't it, of the language and all the capabilities we're getting with SysML v2. But this is a time also to reflect on all the work that went into getting to where we are. And whenever you have a large new language like this, people are going to look at it and say, why did you do that? Why did you do it that way? And there was a lot of thought and also a lot of compromises and trade-off that went into the language to get to where we are. We think we've made a lot of good decisions. We have opportunities now with the finalization process to address some of the issues that are coming up in implementation. So I wanted to let you know with this part of the presentation a little bit about the background of how we got to the language and invite you to be involved in submitting issues and helping us make the language even better before it gets finalized. So some of you may have heard of the second system effect. This is a term that was actually introduced by Fred Brooks in his classic book, The Mythical Man Month. And this is a shortened definition from Wikipedia, but it's the tendency of a small, elegant, and successful system to be succeeded by an over-engineered and bloated system. And the reason for this is that when an architect or a team works on their first system, they are very careful because they're not sure how to proceed, so they're cautious, and they defer a lot of things they would have liked to have done but they think are too hard. When they get to the second system, it's, we know now how to do this. We're going to add all those things we left out before, and suddenly the system becomes bloated, it no longer has a consistent design, and it often fails. And then you get to the third system, and the architect or the team has learned how to compromise. Well, the question is, how do we avoid, how we believe did avoid this second system effect with SysML v2? And there were a number of mitigating factors. One of which is that this really wasn't the second system for at least the leadership on this. Yes, it was the second version of SysML v2, but we'd all been through UML2. We'd all been through some of the succeeding standards like the UML, executable UML specification, and multiple iterations of SysML 1x. But we also took a lot of pains to set up a process, to set up a team, a submission team and a process for that team where we were very user-focused on what we put in the language. We had very ambitious requests for proposals, but we tried very hard to make sure that in responding to that, we vetted what we put into the language. So I'd like to give you a little background on that. On the SysML v2 submission team, as Sandy said, Sandy and I were the leads of the submission team. The submission team itself was formed to respond to the requests for proposals. There were actually 2 requests for proposals. The first one came out in December 2017. That was for the language itself, and the second one was a little bit delayed for more discussion. It was for the services and API that came out in June of 2018. The submission team was formed immediately when the first RFP came out in December of 2017. And it grew to a very broad team. By the time we were done, we had over 200 individual members who had participated in over 80 organizations. And we developed submissions for both the RFPs coming out of this team. The final submission was this year, and as Sandy showed, we are now proceeding to finalization, and we'll have the formal spec out next year. So when I say 80, it was a diverse group. This is the list. There's actually 81 on this list, I counted. And you can see from the colors that we have academic organizations, tool vendor organizations, government representatives, and a large number of end user representatives also. So we really had a cross-cutting set of organizations from the community. But that could also be a recipe for disaster, right? So here we have ambitious RFPs for a major rework of a major language, and we have this huge team. Now, it didn't start huge, but it did grow very quickly from initially, it was like 10, 12 organizations to 80 over a period of 4 or 5 years. So how did we manage that? Well, believe it or not, we tried to be as agile as we could. We set up a process from quite early on where we actually did a pilot implementation, as Sandy has mentioned. But the pilot implementation was not just something we did late in the process or after the fact. This was how we drove the development of the language. And we set up, within the first year, we had set up an iterative process where we delivered almost every month, we skipped a few, but almost every month for 5 years, we did a release of our pilot implementation. And this was the process that we went through here. I'm not going to go into entire detail, but you notice we had what we called our track teams. We had 6 tracks. Track 1 is the project management track. But track 2 was our requirements V&V track. That was our user representatives. So they looked at the requirements, came up with a set of validation cases, which even before we had the language, were mock-ups of what they wanted to do with V2. Not just what the requirements said we needed to have in the language, but what the users wanted the language to be able to do for them. We took those validation cases, and that was a major input into our design approach. Those validation cases were also developed incrementally, going through areas of the requirements. And as we did that, we designed the meta model. That was track 4, our meta model development track, and that fed into tracks 5 and 6, which actually did the implementation of the language in track 6 and of the API and services in track 5. And then that also, this started a little bit later because at first we had a requirement to do a profile, a UML profile for V2. Tim here, you can't see him online, but Tim Valkins was key in trying to do that, and we found out it really was not going to work out well to try to do a profile tailored to V2. There was too much difference we wanted in the language from UML. That was one of the issues. We wanted to move away from UML, so it was hard to do a profile. So instead, we repurposed track 3 to work on the V1 to V2 transformation, which was also a lot of work and is still going on in finalization. But the key thing here is if you look at the bottom there, you can see the pilot implementation had the incremental release, the visualization feeding in, the repository, and that fed back to track 2. And we had deployment out to Jupyter. You notice the implementation, the development was actually done in Eclipse. So it's an Eclipse-based tooling, but we were able to package that up and develop what was called a Jupyter kernel, for those of you who know Jupyter Notebook. And that was our major vehicle for having our users use the language, and they did. And they re-implemented the validation cases and quite a bit of other work. And as you'll notice, we had the textual notation. If you're going to use Jupyter Notebook, it is defined around doing textual languages, doing programming languages. That was something that was a real plus early on when it was much harder to develop prototype graphical visualization and graphical editing. Having the textual notation early on allowed us to do this cycle. And I'll have a little bit more to say about that later. And these are our milestones starting December 2017 all the way to our final submission. What I want to highlight here is these points. You notice not only did we have this monthly iteration, we had a series of internal reviews that were very influential, especially the August 2019 review. That's where we really, for the first time, went from proposing ideas for what was going to be in the language and sort of saying, yeah, this notation isn't really what we want. We just want to check out the abstract syntax. When we got to that first internal review, we went to the users and said, for a small subset, this is what we're proposing. And that was when they started using it. So we were about 1.5 years in at that point. And at that point, that's when we showed them Jupyter Notebook. We had that integration, and it just took off after that point. And that was where we really start getting the iteration. In February 2021, that stakeholder review, that was where we focused on the graphical notation, and that's really got started because it was never supposed to be just a textual language. It's a textual and a graphical language, and the graphical language is just as much as in V1. It's just we also now have the textual notation. So by February 2021, we were getting a lot of input on the graphical notation. By the time we got to September, we were actually later than what we had set out in the RFP. We actually had targeted for September 2022. It was actually earlier. It was like the first revised submission in August 2021 was the RFP date. So it got delayed. We had more revised submissions. And we finally delayed it again to December. The third revised submission was November 2022 for review at the December meeting. But in the September meeting before that, we said, look, we're just about done. We did a 2.5-day review at the OMG meeting in September 2022 of both the underlying kernel foundation and SysML and got a number of issues. It turned out when we got to December, we said, you know, we basically have the language done now, but we need more time really to work on the SysML spec document itself and get that together. But what we said was, look, we made a commitment to deliver in December, and there were vendors implementing and users starting to use it. So what we said was, we will not make major changes to the language. We're writing the spec and getting that in shape. If we need change to the language, we actually set up an internal change board. So we let the users, in this case, it was mostly the vendors, we let the vendors say, if you're implementing this, we will let you know of any changes, and if you think it's too much, we won't do it. So again, we were very responsive to our community throughout this whole process. And then we did get the final submission done in February. So that was the process we set up. Coming out of that, I wanted to highlight a few major design principles. And these are really fundamental to how we structured the languages. And they all were things that Sandy showed. So I just want to highlight some of the things and how they were foundational principles in the design. First of all is consistency. Sandy said the example that he showed was the definition and usage. Look at SysML v1. SysML v1 had all these terms, and to some extent that was because there wasn't a conceptual consistency coming out of UML. Things were added on in SysML v1 over time, like interface block and proxy port. What does that mean, right? Why are those related? It was actually, we felt, a rather gutsy move to rename all this. We were actually quite trepidatious. When we went into that August 2019, we actually had the old names. So our original notation had block and part property, had activity and action. We had the old names, we carried those over so people would be familiar with it. As we went on, it was like, no, we don't want to use interface block. We don't want to say interface part. So we had part def and or port def and port property, port def and port usage. And when we got new things, we had like analysis case, definition, analysis case usage. So we started seeing how nice this was. And it's like, we've got to do this consistently. Consistency is important. We put in that new notation. Somewhat to our surprise, everybody took to it. In fact, I did a presentation just a few weeks ago where I showed this slide. Along with a bunch of other stuff, I had more than one people come up and tell me, the most important slide you showed was this slide because it shows that you put the thought in, and all these things where people keep asking us about why do you use the terms in V1 is now so clear in V2. And this is just an example of where we've tried to keep that consistency. So yes, the language is bigger, but it is more consistent, so it is actually easier to learn, not harder. The other really important point here is you get consistency, and once you start being consistent, you start seeing much more clearly how you can unify what you thought were different concepts. Now that happens both because you're trying to think of them consistently. It also happens because in moving off UML, we were moving off a language which had been built up really by aggregating different ways to do things. The model of behavior and actions is different than the model of behavior in state machines. The concept of how you do subsetting and how you do other specialization is different. Things had just come in from different areas. We started seeing some real opportunities to unify our concepts. So for instance, one of the things is that we found, specialization is still there. You can specialize blocks in SysML v1. We can specialize part definitions and other sorts of definitions. However, what we found was that actually we can take this concept of specialization. And when you have I'm sorry, that's not a part def on the right there. That should be a part usage where it says defined by. That was, I didn't change that one. So that's supposed to be on the right. A vehicle part usage, a part vehicle is defined by a vehicle definition. And then we have the vehicle has 4 wheels. We've got a specific vehicle usage where we have the front 2 wheels is a subset of the four wheels. And then we have, on the wheels, we have a set of lug nuts. And for the front wheels, just the front wheels, we have redefined the lug nuts so that there is specifically 4 lug nuts on the front wheels. Now, why are those kinds of specialization? Well, I can give you all the details semantically, but that's not the critical thing. The critical thing is that it means that the properties of the things on the left are inherited by the properties of the things on the right. And that's the fundamental concept. And as we'll see in a moment, that means I can further refine. In a usage, I can refine things from the definition. In a subsetting of a usage, I can further refine the properties. It's really powerful, and it leads to the idea of usage-focused modeling. So that was one critical unification. Another critical unification is that in UML, the relationship between a part and its subparts and an activity and its actions is completely different in the meta model. In our case, everything is these feature membership relationships, which I'll talk about in a minute. Actions are features of their containing action definitions or action usages, just like parts are features of their containing part definition and part usage. This is really powerful because what it lets you do is it lets you mix and match much more easily, and it lets you have further unifications, like the idea of here we have 2 actions communicating by a flow between parameters. Again, in UML and therefore V1, the flows between actions were object flows. Completely different semantics, different syntax. They might have looked like arrows. Actually, they didn't look the same as information flows between directed features on ports. Completely different. They're actually exactly the same thing. The parameters on actions are the same thing. They're just directed features on actions, just like directed features in and out features on ports. So that's unified, and that means you can, when you perform an action, as Sandy showed, you can take the output of that action and just flow it right into the output feature of a port and send it out on a connector. And the semantics works and the syntax works. Now, one of the benefits of that is this specialization in context, which is extremely important. So let's go back to that example I showed you with the same mistake, because it was cut and paste, where that part depth vehicle should be a part usage, should be a part. But the idea here is that you can specialize a feature in the context of their owner. So in the context of that vehicle usage, it should say vehicle 1. So that, say, in the context of vehicle 1, I have now said that it has 2 front wheels that are a subset of the 4 wheels overall that it inherits. It has this overall set of 4 wheels that's inherited. It is subsetting that and says 2 of those are front wheels. In the context of the front wheels, I can further now refine things. So I've added here an attribute to the lug nut, and I say lug nuts actually have a torque. You notice the little bar here. This is a redefinition on the bottom. That means I have not just specialized, but I have redefined. I've said for all the front wheels, I have redefined what a lug nut is such that there are exactly 4 lug nuts, and each lug nut has a torque equal to 20, Newton meters or whatever, the units on torque. The important thing is I can add more of these. So now I can say there are 2 rear wheels, and those 2 rear wheels have 6 lug nuts. And the torque for those 6 lug nuts is 30. Now think about how you do this in V1. Remember Sandy talking about you can only specialize blocks, and you have to go back and forth between blocks and features, blocks and features. You have to, in V1, you have to specialize it. If you're going to do this, you have to specialize it on the block side and create new definitions just to be able to bind different values here. This confuses people a lot. If you do it on an IBD, people don't realize that an IBD in V1 is basically a class diagram, not an instance diagram. And if I change the torque in one view of a block, it's going to change it everywhere. And it's very hard to contextualize. This is one of the critical things that we needed to do in V2, but it opened up a lot of power and capability and a whole new modeling approach. And we have the textual and graphical notation, right? Sandy showed this example. There are corresponding textual and graphical notations for each language construct. It's very parallel. There's a comprehensive expression language also. So now that is part of the standard. It doesn't have to be added in by individual tools. And textual notations can also be used consistently on the graphical diagrams. And that means you have an opportunity in your tooling to have a complete graphical representation, have a complete textual representation. Tools are working on getting those synced up, or you can go back and forth and have a graphical representation, go in and like expand it and say, oh, inside this, I want to have it be textual. Oh, now I want this piece to be graphical because the textual annotations and the graphics are consistent with the full textual notation. Very powerful approach that we're starting to see the vendors actually are going to be building into the next generation of tools, which hopefully everybody will be seeing soon. Now, I know there's some people who are thinking, and I've seen some of the comments come up online, will systems engineers really use a textual language? Well, they don't have to. You can still do everything in the graphical language, number one. Number two, I'm an engineer, but I've been a programmer most of my career, so I'm very comfortable with the textual notation. And really, we started out with a textual notation, like I said, because it's much easier to prototype and do the iterative approach to start with typical domain-specific language tooling using a textual notation. What I found out, and what we found out consistently over the years, was there is a large segment of non-software systems engineers who are really taken with the textual notation. Yes, once they get a big model, they want to see it visualized, but they don't mind using the textual notation to enter it and even to edit it. Now, yeah, if you have a big state machine, it's going to be easier to edit the state machine and maybe an activity diagram. But I've just been amazed at much bigger fraction of the community than I expected has taken to it, and the younger generation even more so, who are already being trained, even as systems engineers, in software tooling, like Jupyter, which is basically an engineer's software tool, having the textual notation, and ultimately being able to integrate the software side in Jupyter Notebook with the modeling side in SysML v2 seems very natural to the next generation. But even the older generation, not everybody, but a much larger fraction. So I think it's been a big win for us to have this textual notation. All right, those are some of our basic principles that really you see consistently in the language. So we have to be consistent about our consistency. What I want to talk a little bit now is some of the more, let's say controversial, or some of the design decisions we had to make where we needed to make trade-offs, and we are seeing the consequences of those trade-offs, and these are under discussion. So these are the ones where people might say, why did you do it that way? Well, let me give you an idea of why we did it that way and why we welcome further discussion, but on the basis of the fact that we didn't do these things without a lot of thought. So the first one I want to talk about is this idea of reified relationships. Isn't that a good alliteration? Reification basically means you are giving identity to the relationship as an object. In our case, all these relationships that I'm showing here are actual model elements in the model. So for instance, you've got, not unexpectedly, when you have one package import another package, that's a reified relationship. That's true in UML and SysML v1 also. However, when you have that package has in it this part definition vehicle, that owning membership is a membership relationship. It's an actual model element in the model. That's not true in v1. In v1, you just have a set of owned members of a package, and there is no relationship like an import relationship. So you have to handle them differently. Tooling needs to handle them differently. In our case, you get down to the vehicle, and even though you see there maybe familiar black and white diamonds, Those are not associations. We do have what we call connections, which serve the purpose of association blocks and connectors. But these are feature memberships. They're a special kind of owning membership where you have a feature, an owned feature, which is like a property. So equivalent of a part property here is a part usage, like that engine, that is owned by that vehicle. It is a feature of the vehicle. The black diamond means it's compositional, and the white diamond means it's a reference. So we're considering the driver not to be a composite part of the vehicle, but referenced by the vehicle. And you have the feature typing as a kind of specialization, as I showed before. Now, I've broken this out. There's more shorter hand notations for that, but in the end, I wanted to show you that what you get from this is a graph structure, a consistent graph structure for navigating the model. Now, if you're a computer scientist at least, you know what I mean by a graph structure. It is basically a structure. We have nodes and edges. In our case, you've got these relationships are the edges, and the non-relationship elements are the nodes. And we have a rule, a design rule that says every non-relationship element can only be connected to another non-relationship element through a reified relationship. Now, we do have derived shortcuts and whatnot, but the underlying model is this very consistent graph structure. And that's the rationale, right? And it was proposed from the group that was really thinking about how to handle this in the API and the tooling underneath. There is, however, a trade-off. Yes, you can navigate better, and if you have a good graph database technology, you should be able to handle dealing with large graphs. On the other hand, there are scalability issues with graph database technology, and there will be other databases, but what you end up with is a lot more model elements, right? So if you're using a relational database, say, you're going to have not just a table of part definitions, you're going to have a table of part definitions, part usages, and another table that's going to have the properties of the relationships between them. It's not just going to be a simple reference anymore. So that is the language tool vendors then said, oh, that's going to be a real problem. They are working on it, though. But this was where there was a discussion and attention. We finally decided that the regularity of this was important enough that we were going to make this trade-off, and that became a fundamental part of the language. Now, that did have other implications. So I just said, oh, that was a very general. We have more compact notations than what I was showing there. I was showing the full graph structure actually in our notation, but you don't always want to write it out that way. And there are some simple conceptual notations from the user side that actually underneath are more complicated. So in this case, right, in SysML v1, I can say a block or a part property can satisfy some requirement, right? So this is in SysML v2, I've got the engine part, and it's satisfying an engine power requirement. Conceptually very simple. It looks like one relationship. Well, in reality, what that expands into underneath is not that simple. What we have specified for this is that you take the engine power requirement, you specialize it with this special satisfy requirement usage, which then binds it. It's subject. Every requirement has a subject that it's about, and you bind that to the engine. Well, why did we do it this way? Because it has a meaning. In SysML v1, satisfy is just a dependency. Yes, it's simple. It is one element that relates the thing that satisfies the requirement to the requirement. It has no formal meaning, and you can't give it a formal meaning because it's just a dependency, and dependencies don't have any semantics in UML. They're just a syntactic way to add a note to something. What we have here is a pattern that actually has a meaning. What it means is that if I take that requirement is parameterized by its subject, which has to be some kind of engine, and this binds that specific part and says that part, when you plug it into that requirement is satisfied. And what does it being satisfied mean? Well, Sandy showed you. It means that the constraints, the required constraints of that requirement are satisfied on that engine. This is similar to what you see in, say, a macro expansion in a programming language, We've kept the surface notation simple. We've mapped into underlying capabilities in order to give it an actual analyzable, checkable semantics. So that is the rationale here. Maintain the simple user concept, avoid the use of meaningless dependency relationships, and make sure that we build on our underlying semantic primitives. The trade-off is the simple notation hides the complexity. So now we already said we were going to have more model elements because we have reified relationships. Now it looks simple. It looks like there's one element on the left here, on the right. If you look at it on the left, what you actually have is 7. When you count 1, 2, 3, 4, 5, 6, 7, when I count the lines as well as the boxes, we have 7 elements to capture that one conceptual relationship. And we're still working out. We have cases where we've been able to package this pattern and have it inherited and parameterized. There are other cases like this one where this actually gets expanded into the actual abstract syntax. So if you look at it in the repository, yeah, the navigation has to go around this. So that's a topic for discussion. The trade-off here, we got a benefit from the user language side. We have now a negative from the repository side, and how do we provide shortcuts and other ways to deal with that? And that's a discussion that's going on. Fundamental to our approach also is this idea of semantic library models. I just talked about, well, we're giving it semantics. Well, what does that mean? What is the meaning of meaning, right? Semantics is about meaning. So what do I mean by that? Well, what I mean is we want to formally ground our language. So when we do analysis and simulation and other connect to other tools, we have a consistent standard meaning for our SysML v2 models. Now, you can say in SysML v1 there's a lot of words around what things mean, and in UML there's even many more words around what things mean, but they're just English words. And we've already found that people don't interpret those words consistently. That was why in the UML world we created a parallel set of executable UML and precise semantic specifications. But they were added on after the fact and only did a subset of the language. We set out with v2 from the beginning. Everything in v2 is going to ultimately be grounded in a formal semantic. All right, we do have dependencies. It is possible at v2 to still use dependencies, but we really have tried not to build that in as a fundamental capability for things like satisfaction of requirements and allocation. We don't use dependencies for those anymore. If you want to put a dependency into your model, you can. But other things, including allocation, satisfaction, verification, all have a semantics. And if you go down to the basic semantics of parts and actions, that all ultimately gets grounded. Now, when I say it's grounded in formal semantics, you're not going to want systems engineers to be thinking necessarily in formal mathematical logic all the time. So what we've done is say, all right, what you mean when you're doing a part definition, and that part definition vehicle has a part that's an engine. Well, I can explain it to you. I can say engine is a subpart of the vehicle. It's compositional. That means if the vehicle is destroyed, then the engine is also destroyed if it is connected to the vehicle at that time, and so on. And I can talk about parts having actions, what it means for them to perform actions. Well, when I'm talking about it, I am using a terminology. I am talking about the relationships between things. That's just something that could be modeled ontologically. And we have the capability within SysML v2 to actually model those concepts. So we have a library model in our package called parts in a standard library. That library model, this is a very small subset, but it includes a part definition for part. What does a part mean? Well, a part can have subparts. There can be a generic concept. That's this on the left there. The thing called parts is the most general feature. It is the set of parts, multiplicity 0 to star. It's also non-unique, and any subset, any set of parts, any part feature is going to be a subset of that most general parts. And in particular, a part can have subparts, and that subparts for each part is a set is a specialization of that most general feature parts. So that's the idea is, and it is a little funny, right? I have a part definition for part. Well, what does that mean for a vehicle? How are these related? Well, they're related through these implied relationships. If I don't have a vehicle specialize anything else, if I have a car specialize a vehicle, well, okay, a car specializes a vehicle. A vehicle, I didn't say specialized anything else. Well, it is implicitly a specialization part. So what this says is a vehicle is a kind of part. It has an engine in it. An engine is a specialization, a subset of the subparts of that part. Happens to have one engine. As I showed you, it had 2 wheels. This means if you can ask any part what all its subparts are, and I'm not talking about in a repository syntactically, I'm talking about the actual instance. If I have Sandy's vehicle, and I say, what are the subparts of Sandy's vehicle? It will say for that vehicle, what the engine is, what the 4 wheels are, etc. They are all a subset of this general idea of subparts. Now, we call those implied relationships because they are not in the actual surface model. Not only that, when you parse either graphically or textually the surface model, they're not in there either. They are derivable by the rules of SysML, and we have a set of formal constraints. If those constraints are satisfied, there's rules for adding the implied relationships. A tool doesn't have to do that. However, a tool does have to take them into account. So the rationale here is this is an ontological semantics for parts, but it's also true for actions and every other feature, and it is an extensible library. So Sandy mentioned our language extension approach. Stereotypes are a syntactic extension mechanism. We have metadata annotations, which is a syntactic mechanism, but we also have semantic metadata, which allows your annotation to add an implied relationship. So you can actually use this same mechanism to define your extended language and extend the semantics of SysML v2 as well as the syntax of SysML v2. But this is another thing tools need to account for. We intentionally said they don't have to physically put it into the model, and there is an interchange option. It's similar to derived properties. There's an interchange option on you can interchange with or without the implied relationships, and you save a lot of space not putting them in there. However, these are, in this case, implied specializations, which means they imply inheritance. They imply that that vehicle actually has a feature, inherited feature called subparts, that it is subsetting, which means that when you are checking things, you have to take that into account. And that is a new thing that tools have to do. That means the tool has to know the implied relationship. It either has to physically put it in, and it needs to take that into account for inheritance, name resolution, and also for validation checking, because the validation constraints assume the applied relationships are there. And in the pilot implementation, this was a big area to work out. That's one reason we did the pilot implementation, not just to provide feedback, but another reason was to prove it could be implemented. Because if we couldn't implement it, we didn't want to do it. And we knew if we got to the end with these hard things and we didn't implement it, the vendors would say, this isn't implementable. So now we can say, by the way, we implemented it, so you can too. And that's what they're looking. They're looking at the pilot implementation and saying, how is it done there? Do we want to do it that way? How do we make it better? How do we make it more scalable? But we at least have a reference that it's doable. So the trade-off here is that, again, this is harder for the tools, but it makes it more powerful and easier for the users. You can see that was the trade-off that went that direction. Conclusion. So the conclusion basically is that we didn't do badly for a second system, right? We ran the SST for over 5 years. We had no significant conflict on it was pretty amazing. We lost no participating organization. Sure, some had less involvement at the end than they did at the beginning. Not to be surprised, some came in for specific things, but nobody, and about over half of them, we had a formal teaming agreement. We had some that were just there doing review, and they could have withdrawn from that teaming agreement, which they could have if they were upset and for IP reasons. Nobody did. So it was a very successful team. The pilot implementation was released with a few gaps, but almost every month from November 2018 to February 2023. We haven't released since February because we've been in sort of this transitional period, but we will be restarting releases and supporting the FTFs over the next couple months. We submitted specifications, and we presented this at the OMG because you have to say, how did you do? We didn't meet 100% of our requirements. With large RFPs, it's generally the case that there are reasons not to meet 100%, but we met about 80% of the RFP requirements across both RFPs. And that's, for something of this complexity, we were actually pretty pleased how much we had gotten into the language with our design principles. And there's already a V2 user community, right? The pilot implementation, the third thing it did, besides providing internal feedback to the design, besides proving the implementability of things, people started using it. At first, we were only doing quarterly public releases and at OMG meetings, and basically otherwise the monthly releases were internal. Well, after I think about a year, we went to monthly public releases with full open source licensing, and we actually have people picking up the pilot implementation, building other things on top of it, other tooling on top, open source tooling on top of it, packaging it for deployment, and using it on actual projects, knowing that, yes, it could still change, right? But people actually started using it with this pilot tooling on actual paid projects, which was beyond anything that had happened certainly with UML2 or SysML v1. And there's great interest now in moving to v2 in the wider community. That's why you're here today. But there were trade-offs, and we want to be honest about that, right? And that's still part of the discussion. It's not just a simple evolution from v1. It's not like you're just going to take your v1 models and move a few things along and they become v2. As Sandy said, working intelligently on the migration v1 to v2 is going to be making this work and allowing the entire community to have the advantages of v2 without losing all the investment that was made in v1 for almost 15 years now. SysML v2 is definitely bigger than v1. Now, if you look at the spec, yes, it's bigger, but remember, we didn't base it on UML. So you have to compare it not just to v1, but v1 plus UML for SysML. But it is still bigger than v1 plus UML for SysML because we have new functionality. We have things like analysis cases and validation cases. We have a full expression language and abstract syntax. So it is bigger, and we also have extensive model libraries. Now, we think we get a lot of advantage from that, but it means it is a big language to implement. So it is not easy to implement. As you say, we've made a compromise, for reified relationships. That helps the repository implementation, but makes some of the other tooling implementation harder. We tried giving feedback from our users to make it a very usable language. Well, sometimes that makes it harder to implement. The name resolution rules are hard. The implied relationship rules are hard. We sometimes have an expansion of the abstract syntax that's not obvious from the surface syntax. So it's harder to go back then from the abstract syntax back to the surface syntax. So it's not an easy language to implement, but many implementations are in progress. So either these vendors have either all announced already over the last year that they're working on it or gave me permission to list them. And so you see the big Dassault, IBM, PTC, Sparks, all working on it. And you have other vendors who are secondary tool vendors or digital industry players, Intercax, Sandy already mentioned Sandia, but Siemens and Ansys have publicly talked about it. Siemens had a press release not too long ago on collaborating with IBM, including SysML v2. And Ansys has, God knows how many. We actually had, I think, 4 separate companies that are now all Ansys on our team. So in a sense, we did lose some members of the SST because they were bought by Ansys, but we didn't lose any participation. And they are working across a number of product lines on SysML v2. So that's where we are now, and I just wanted to end by telling you the pilot implementation is still available. It's on GitHub. We have a release repository you can go to. You can install it either for Eclipse and or for Jupyter. There are the open source repositories are all there. There's the release repository, but also the development repositories are there in open source software. But if you want to get involved, I would strongly recommend that you go to the SysML v2 release group. It's actually still very active. Unfortunately, the SST team, because we're in transition, hasn't been as responsive lately, but again, we want to get back to that because we've had very good interaction and we've really built up an online community now, and we have a number of people coming back and asking questions to get going. So I strongly recommend, if you're interested, to join that Google group. You have to have a Google account. You have to request to join with your Google account, but we don't turn anyone down. It just may take me a little while to notice, since Google stopped sending notifications, to notice that somebody put a request in, but you will get in. And with that, I want to thank you